here in Germany. Really, a lot of us do this alongside my day job, which is DevOps recruitment as well. Actually, next slide, please.
Sorry.
Actually, apologies.
You showing everything to everyone.
Do you have an insight of the agenda? So the first half an hour for networking. Oh, it's just me.
That one? No.
At 6:35, we'll start with the lovely Nalton, doing the first presentation, followed by Abner, who is doing the second presentation, and then Leo, who's doing the third. We have got snacks and drinks. If you don't know where the toilets are, they're just out the door to the left and behind. And at the end, we will have pizza and at capacity. Help us have any drinks if you would like as well. And I think the clicker is still working.
Yay.
So yeah, how to make our agenda. I'll let the panel introduce themselves as well when they do their presentations, but in short, from Nigel to Current Architect at North Cloud, Leonard, who recently got promoted to Senior DevOps Engineer here at Summit, congratulations, and Batman is a Senior Site Reliability Engineer at Summit as well. Cool. Just to give you a little bit of background about women in DevOps, if nobody's ever heard of us before, this is something I do alongside my day job at Trust and Solar. So DevOps was founded in London in 2017. Trust and Solar is a recruitment business, which is part of the group called Telemetry Group, whose mission is to build diversity, create inclusion, and encourage workplace innovation. And we have a number of different offline communities. I feel super privileged to be able to be part of this DevOps community. So you will hear today and allow you all to share your ideas as well. But our aim is essentially to be able to ensure that underrepresented voices can inspire the future leaders throughout all areas of technology as well. And as you can see, we are totally as well. Please reach out to me if you've got any questions on LinkedIn afterwards or my email as well. And now I would love to hand over to the lovely Miriam, who is Head of Special Operations of IT here at Summit. Thank you so much for being our host.
Hi. Is this on? Yes. Okay, cool. Welcome, everybody. I'm really, really happy that you made it here tonight after your work. We highly appreciate it. I just wanted to lose a few words about the lovely SumUp office that you're in today. So for those who don't know SumUp, we started with this little tiny white card readers that you see in many stores around Germany and worldwide. And we're a global fintech company. And we do much more than these card readers. We also do online payments. We do the point of sale systems. We have a web shop now. So there are like many things that we do additionally on the top of this. And just to mention very shortly, we are also hiring DevOps engineers, and we are looking to increase our diversity. So we are really happy to host you here. And if you're interested, you can talk to us or look on our career page. Otherwise, I wish you a lovely evening. I will also be sticking around, so happy to small talk later and answer further questions. And looking forward to the amazing speakers and the topics, and hope you enjoy the evening.
Thank you. So we've got 3 presentations straight after each other. Just after each presentation, there will be a Q&A. You can ask here directly, put your hand up. Equally, if you would rather ask your question via the internet, we have a Slido, which is a little bit blocked. It is slido.com/WID October, and you can just ask your questions as they go along. Here we go. But cool. I'll now hand over to the wonderful Nadia. We can start working again. Okay. Hello. Hello, everyone. Let's check that the sound works fine, that we see each other, that we can change the slides. I think we can start with the first one. Yes, so welcome. I should also like the first welcome everyone. I hope that all our talks will be very useful for you, and you will find out something new interesting. Several words about myself. Currently, I'm working at North Cloud as a cloud architect. But before that, I had several positions, including Java engineer and Python engineer, and I also participated in the OpenStack Telemetry project. So all this observability, monitoring, telemetry activities come to me throughout my career. And so now I finally decided that, okay, I have enough knowledge to share a little bit. So let's get started. Our agenda today is that we first will talk a little bit about observability in general. Then we will discuss the distributed tracing, and then we will try to understand how auto instrumentation works. So I think everyone knows that in modern distributed systems, you cannot really know what's going on without really deeply tooling internally. So it's, as it is written on the slide, that cloud-native technologies, they must be observable. So it's not a question anymore if you implement observability or not. That's a must. We should all live with this fact. And all communications with modern systems, they happen like the processes. So you cannot just deploy, you cannot just test, you even cannot just create documentation. That doesn't work anymore. So you need to do it systematically, you need to continue with that all the time. So it looks like a process, right? So you need to have this again and again. And observability tooling is not an exception. So it's not something which you can implement and forget about it. That's a process, as everything in this kind of system. But besides that, it doesn't work. Apart from that, I would like to tell that observability is a little bit more, in my opinion. And I'd like to remind you of pets versus cattle analogy, which we have for infrastructure. In infrastructure world, we have this goal that we shouldn't have any non-interchangeable resource in our system. So that's the goal. Again, I know that there are some exceptions for that, but the goal is to have everything be creatable. So the zero downtime, we all need to have a new resource, a new database, a new virtual machine or container, and so on and so forth. So that's the cloud basic. But if we think about this analogy applied to operations, we can see that actually if you have this observability data, you can have, as fully as possible and as fast as possible, get an idea about your system, because you never know what's actually happening there. And also my point is that that's absolutely fine. So as you expect bugs in your application code, you should expect that you don't know everything about your system.
that's expected, but you should simply leave it that way. The system. Instead, we should have this lasting and available source of knowledge, which everyone can use and everyone knows how to use. That's observability. And another thing is that I really like this quote from a very good book, which I really recommend. That observability is this capability to allow human to ask questions. So you always need to know what to ask, and different people can ask different things. So, for example, operators, one can ask one question, developers another question, and this question can be completely different. That's, I think, it about this general part. We can go further, yeah. So,
Can we swap microphone?
Yeah.
Just people online can't hear.
Okay. You swap with what?
That's the microphone.
Okay, then do you hear me? I should speak like this? Yeah, really? Okay. After this introduction part, let's get back to this real practical things. And let me remind you so-called observability pillars. And I think that everyone already knows 3 of them. They are metrics, logs, and traces. But there are 2 more which I'd like you to pay attention to. Visualization is a crucial part. And without visualization, the first 3 points are just data. So that's simply data. You can collect gigabytes of logs and traces, but if you do not know what to do with them, it's just useless. And the last point is that human is our observer, right? So observability doesn't exist without observer. And that's the main difference from monitoring. So the word monitoring has been used widely before, and now observability is the most fashionable word, but that's only because we changed the focus a little bit. So monitoring is more about automated way, maybe even to fix the problems or at least get alerted about the problems. But observability is a little bit more, as I already said, that's a source of knowledge. That's why we really need a human here. Next slide, please. Okay, if we have these problems, let me also take my glasses.
Not an event without technical issues, right?
that's the process, right?
Okay.
Everything is a process.
And then also hold that one. Sorry.
So this one and this one.
Yeah.
Fine, okay. Some more challenges. Reminds me of a game. So now I have 3 things in my head. Okay, let's try to discuss now this 3rd pillar, which I mentioned on the previous slide, distributed traces or just traces, whatever. So what do we really need from these distributed traces systems? Why is that important, and why we cannot just get everything from our system and enjoy the data? That's a little bit more complicated. So the very first thing we need is actually to have some infrastructure, some API to put into our code. So let me ask one question to the audience. Is everyone aware of this difference between logs and traces? Who knows anything about it? Okay, good. Yeah, so when, if anyone doesn't know anything, you can think about traces like about logs, but with additional context. And we will discuss it in this slide. But the first thing, as with logs, as with usual logs, when you create your log line in your code, you need to write this statement in your code, right? That I want to write info message in my logs. The same we need to do with traces. So you need something to put into your code first. That's the first step. After that, your code can create some events, and these events are also called spans. One of the options. Then something very important should happen. As we don't just need these events, we need a little bit more. For example, we might need some information about what's going on in our system. For example, if we just ask or send requests to our database, we can additionally put this request in our event. So just to make it easier. Or we also can put some URL information to our event. The same as with logs again. So we can write anything in the logs, we can put something into traces. And the crucial part here is that it's not just metadata, that also this explicit causality references. And that's a very important part because you do not want just to have this event or this log message. You want to know the place of this event in your sequence of events, sequence of other events. Without that, you simply cannot zoom in and out. So when you have this information, you can get details. So you can try to understand what is going on underneath this request. And you can zoom in and zoom out. And that's very valuable property of this distributed tracing thing. And the last part is that, okay, so you have this metadata associated, you have these references, but it's important that you can propagate this information throughout your system. Imagine your system with 10 or more services. And all these services are running in Kubernetes cluster, in some AWS, for example, and on premises. And you start propagating your request in your system, throughout your system. And some services communicate through RPC. Some of them use a message bus for communication. And all these pipelines, they should know how to propagate this metadata, how to keep this very valuable information in your event, in your span. And that's the task for distributed tracing infrastructure. That's how it works. And that's actually a very important task, which is not that easy to implement. Next slide. Yeah, and finally, some pictures. So how does it look like actually? This is the screenshot from Datadog, but it doesn't matter basically. So you can use the same, you can see the same picture in different platforms. But here you can see that, so each colorful block is basically a span. The whole thing is called a trace. And you see that you also have this information associated with this spans. So you have these tags, and you have this information associated with your spans. Each span has this tags associated. I think that's enough. We can go further. Yeah, so now we can think what actually we should do to start using that. So I call this slide intuitively clear manual implementation. it is really not that complicated. That's just example from Open Telemetry. And what we see here is that we have, this is a Python code, and we have a server request. And we see that this last two lines about print and return served, these two lines are executed within this span. So here's example how we create it. We see that some attributes are associated with this span. We see the context. So that's basically what we should do, right? But now just imagine that, okay, so you decide finally to implement observability in your system. And so what we should go to every request and add these lines, or what should we do with our libraries, which we do not even have access to the source code. Libraries are very important because that's just, we also want to know what's happening inside this part. But if we take a closer look into this, we see that there is nothing, actually nothing special about these lines, how we create the span, right? So it's just, we get headers from request. We say that it's this kind is server. We get some attributes from request, but actually we can just copy paste the same lines and put to every request. And only this action can already give us some data. So we can really get more knowledge just copy pasting the same thing throughout our code. Yeah, and the same is for Java. So I didn't put Java code here because Java code is not so compact, unfortunately, or fortunately. Yeah, and so if we can copy paste, it means that we can automate this part, right? Maybe we can go to the next slide. Yes, so it can work without this manual implementation. So we can really automate this copy paste, and that's what auto instrumentation does. So that it is called auto instrumentation. And in some languages, we can do it easier. In some languages, it is harder. But the idea is that if you use a popular programming language, it is very likely that you have this option. Thank you. So this is just a 10,000-foot view of Java code execution. And let's first take a look into this Java example. So how does it work there? So first, the source code got translated to the bytecode. Then the bytecode is executed within our virtual machine, Java virtual machine. And only after that, we have this machine code. So that's this Java portability, right? So that's why Java works on each system. And the bytecode actually is exactly the place which are really interested for us. There are several properties which are crucially important. So first, it's a platform independency. Then the second thing is that when we use these jar files in Java, they also contain this bytecode. So even when we do not have source code, we have access to bytecode, and that's just perfect thing for us. The third one is that this bytecode is not just a set of bytes, surprisingly. That's a very well-defined specification, and you can always read that and try to understand how to read this bytecode. And the last thing, which is just, I think the most important one, is that Java has a native support for this bytecode manipulation. Before they had only this Java reflection thing, which you could use for this Java magic. now it's this official Java agent, and you can use it to manipulate bytecode. And that's super interesting because you basically have two languages in one. You can create Java source code and then manipulate this code, or you can just play with bytecode if you are real IT guy and want some fun, right? Yeah. So how does it look for end user? Next slide. That's it. That's the only change you need to do to instrument your Java code. So your task is just to add this Java agent into your path, and you can right away, you can enjoy this auto instrumentation. It might not be perfect, but it's the great start for distributed tracing. You can always try that and see what you get from that. But of course, when you see something which looks like a huge value with no effort, we know that we just need to think again about it. Next slide tells us what's actually the problem. And I think that we can understand that even without this warning. So what happens here? You basically allow somebody, some code, external code, arbitrarily change your everything. So change not only your application, but also the code of the libraries which you use. So it's a huge security risk. And if you decide to do that in production, then your security specialists should be aware of that. So you should really keep track of this jar file, which can do whatever it wants with your system. Yeah, the next slide. Okay, so with the Python, it's a little bit different story, but a very similar one. In Java, we have these three stages: source code, bytecode, and machine code. For Python, it's a little bit different, right? So we can, Python has instruments for changing the code in runtime, and that is called monkey patching. And that's a very controversial technology, and Python engineers do not really like using monkey patching, but there are at least three scenarios where we can really use it. The first one is, as you can guess, it's testing. So when we test Python programs, we do not want to just create this big objects of databases and so on. So we just monkey patch them. The second example is green threads. So it's also very well known. When you use this green threading in Python, you need to monkey patch your standard libraries to make them green thread friendly. And the third example is, in my opinion, is this auto instrumentation. I think it's also a very good scenario when we can really get a lot of value from monkey patching. And this is the example of end user, again, how we use it, how we apply auto instrumentation into our code. It depends on the tracer which you use. So I have these two examples for Datadog and for OpenTelemetry. You simply change the way how you run your application, and that's it. So after that, you can enjoy your traces. Yeah. So what we have next? Next we have this nice video. Yeah. So finally, another entertainment. Yeah, so that's the same thing which I already showed you, but here I give more information. So here you can see that you can basically filter your spans based on the type of your service. You also can see that that's what you can get, right? So this is this dependency map, and that's just, you have it. When you know how requests fly throughout your system, you can understand what's actually, what are these dependencies. inside your system. And when you have, when you know how significant amount of your requests fly, you can make this conclusion how your services communicate with each other. You can see this dependency map, and actually this dependency map should be ideally absolutely the same as this architecture. So this initial architecture, which was created before you started your project. That's a great test. And actually, if you are interested in that, you can Google trace-driven development. So that's a very interesting topic I discovered during this preparation to this speech. Yeah, so just as usual testing, just describe what you expect from your traces, which dependencies you expect, and then you will see them if it's really the case. Yeah. The next slide, we can try, we can try the next slide. Yes. The last point is that, of course, it requires a lot of effort, especially when it comes to how you can, and here, when it comes to standards. So as I said, I gave this example already. So when you propagate this context throughout your system, all parts of your system should be aware that actually you are trying to do something with this context. And that's what the community is trying to agree upon. And V3C trace context is the standard which is now being developed. So you can always see what's going on there. And of course, the biggest project in the industry is Open Telemetry. And that's just a must to know for everyone who is interested in observability. Very interesting, and you can find a lot of tasks for every level, so you're welcome to participate. And each big hypervisor, like Amazon, Google, they all have their own implementations of distributed tracing. And as usual, Google was the first one who open sourced their solution, which is called Depper. So if you are interested in this history, you're welcome to read about it, just to know that Google was this first company who open sourced this. Yeah, and the last slide from me is what I actually would like you to take away from this talk, is that, oops, nothing, just questions. Yeah, but so that observability is a must. So you cannot live without that. It's very important. The second thing is that it is very likely that you can get a lot of value with not so much effort. Yeah, and the last one, which I didn't talk much about, but visualization is the key thing. So you cannot get a lot of value without good data visualization. Yeah, thank you. And now we can ask questions, right?
Yeah. Any questions in the audience? Oh, you. Sorry.
Now it's your turn.
Have the book.
Yeah, so you spoke about the human part of observability. Could you just define what is the action you're referring to here? I mean, fix the issue, or maybe I couldn't get that part. If you can briefly explain that.
Yes.
Thank you.
Yeah, so for me, this human part
is, of course, it might be about fixing the issues, but it's also about getting to know your own system. So, for example, now a lot of companies hire some external consultancy, right? And it's really crucial that this new person can understand very quickly what's actually is going on in the system. And that's where this human, for me at least, plays a big role. If you can start doing your job fast, that's also in my opinion, a goal of observability. It should help you to do that. And it's also a very good point where different people from different roles can start communicating. Because when you have this common place which you can discuss, developers and operators, developers and people who sometimes they are different people who test your system, when you can just have this common space, it helps a lot, because usually different departments have different understanding, different responsibilities. So that's about people. Yeah.
So in one of your earlier slides, you mentioned something causality reference. Could you elaborate on that? Because I didn't quite understand what, or could you just show in the overview what it actually means?
Yeah, that's a very, it's not
that complicated. That's just what is the parent of the span and what are children of the span. So for example, when somebody creates a new user in your system, what happens? You need to check your database if this user exists or not. And this action is basically a child of your request, of your initial request. And the idea here is that you should not lose this information. So you should keep track of that this database request was followed by some other request, or previously we had another request, and that's it. So that's why you can build this graph. So you basically need that for this graph view.
So it's like to support like a drill down, to go from the web request to the database, whatever.
Yeah, exactly.
Well, executed there.
Yeah. And more importantly is that it can, so with database, that's an easy, simple example. But for example, if you send requests to some external system, it's also possible to track that if this context propagation works.
I just have one question. So what's the maintenance cost for having the traceability in your systems?
So did I understand it right? You're asking about this, what additional actions are required to support this system?
Yeah, exactly.
Mm-hmm.
You might think of this as a, having traceability as a single point, and then how do you avoid that single point of failure in your whole system?
Yeah, that's a very good question. And actually, I can answer how Datadog does that, because that's what I see in practice. They basically apply the same thing to their services. So it means that, as I said, it should be really deep integration in the system. And with Datadog, it is these agents which they run on internal infrastructure. And basically what they do, they also collect logs, traces, and metrics from their own agents. And you see in your dashboards, you see not only information about your system, your application, but also how your monitoring works, how your observability works. So it's this circular dependency, but it works. So you can see that if something is happening with your agent, then you do what you usually do with when you see the problem in your infrastructure. If agent is dying, then you do something with that. So ideally, automatically.
Can I ask one question? So this is kind of a follow-up question.
Mm-hmm.
So this is more kind of depends upon the scale. Like Datadog can be, a tool in my system which can cost me huge millions of euros per month, just because like having traceability in my system, which is serving at millions of requests per second. So how do you do that in your own engineering team? Do you have an open source tool for it? Like instead of like having Datadog as a tool?
Yeah. So I would say that now everyone goes towards open telemetry. That's open source solution, which can give you the same data as Datadog agents, for example, but the backend for this data can be different. You can use Datadog too. So, for example, but you collect your data with open telemetry agents, but you process your data with Datadog. So there is this different things. You have agents which collects your data, and you have a backend and this visualization, which is separated from that. And that's why you can mix the solutions. And OpenTelemetry gives you this this thing. You can use OpenTelemetry in one place and then whatever for other cases. And if we speak about this big enterprise solutions, currently it's also one of the tasks is how you can mix your different observability backends, basically. For example, with Amazon or Google, they already have the solution for distributed tracing. And your department, some proactive department, they decided to try Datadog, right? So, and now you have what you have again, this problem, what you do not have the one place where you can see everything. And now you need to combine this backend somehow. And there is solutions for that, but maybe that's for another talk.
Hello. Usually with like tracing, either thing is when you want to trace something which is synchronous, like if you have two HTTP services, like to trace them with databases, easy, you did like it in a day, it works magic. But when you go to, when you in your infrastructure, you have like a mix of synchronous and asynchronous calls, the things are getting much more complicated with asynchronous calls. And like even native supporters, for example, Amazon for its own services does not support for some of the services asynchronous tracing. And it just like, you know, trace goes, and then it disappears somewhere in between. So when implementing tracing, like time-wise, usually you spend not a lot of time in the beginning, like integrating it with your main services. And when you go to like more rare technologies, there you can be stuck for quite a long time. So if you have some experience with that, I would like to hear. And yeah, just like seconds comments, sorry, don't take it. Another like nice thing with tracing is usually if you decide to deprecate something, it's a nice, very nice tool for observability to like live watch how your service is going. Or for example, if you have like some very tangled service somewhere and it doesn't really belong to any team and nobody wants to take care of it, and to understand like where to start your deprecation from, like whereas a majority of the calls going to that service, and then you're just like you open your beautiful graph and watch like one by one traces disappeared, and then like, okay, we can fully deprecate, it's gone. Yeah, it's I think like one of other nice things with like having fully traceable system.
One moment. Yes, and for asynchronous calls, yeah, that's a very good point. And I would answer that this is still implementation in progress. So community is working on that. And it's definitely not for this auto instrumentation. So you need some extra thing. And maybe it's also important to say that usually this auto instrumentation is like a first step. And then the next step is that you add your manual instrumentation just on top of that. And of course, at this point, it starts to be pretty hard to continue, because you can see now your issues, you start solving them. So it's very often it requires the whole team working on that. And yeah, it's at this point, it is very important to explain maybe to management that it's really important for your company, for your next projects. And I see for some of our customers that it might be an issue. So because as usual, you have this 80% of things done with auto instrumentation, and then management expect that, yeah, so we are almost done. So why you cannot finish with that for months? Yeah, that's the usual thing. We need to live with that. I say it for the third time today. Yeah.
Perfect. If there are any last questions, we'll get to them at the end. We're just going to move on to the next speaker now, just to be conscious of time. Thank you so
Yes,
much.
thank you. Thank you.
And now to the wonderful Bhavna, who works at SumUp. She unfortunately couldn't be with us in person today, but thank God for technology. Over to Bhavna.
Can you hear me?
Yes. Can you
Okay.
hear us?
Yes, definitely.
Perfect.
Thank you, Antonia.
Just let us know next live, Bhavna, when you need, okay?
Sure, thank you. So good evening, guys, and welcome everyone. As we already know that we are discussing some of the areas of observability, and I am also here to dig it a bit, but before that, let me introduce myself and what I do. My name is Bhavna, and I work at SumUp as a senior DevOps engineer. I recently joined SumUp in summers, and talking about my experience, I have got 7 years of experience in cloud technologies and its areas. And so far, my journey with SumUp is really going great. And next slide, please. So my topic today is understanding how observability can be achieved within the microservices using service mesh. I hope everyone must have heard about service mesh here and there. There are different tools for this, but I'll be mainly talking about Istio for this talk. So if you're running distributed workloads on Kubernetes and thinking how you're going to manage and observe the microservices at scale, then service mesh is what you're looking for. So next slide. Yes. So today we have the following agendas, as you can see in the screen. We'll be, as I said, we'll be mainly focusing on Istio. So I'll give a short description of what is Istio, why we should use Istio, the architecture, monitoring stack, and the observability part, and how you can use it with your infrastructure to manage your microservices at scale. Next slide. Cool. So what is a service mesh? A service mesh is a dedicated and configurable infrastructure layer which you can add with your Kubernetes workload. It gives you capabilities like observability, traffic management, reliability, security. And the good part is that you don't have to modify your application code. Next slide. Okay. The main question here is why we should use service mesh. As you can see my screen, there are certain features that service mesh comes with. It's intelligent routing, access control, rate limiting, circuit breaking, observability, and many more things. So the service mesh captures all elements of service to service communication as performance metrics, and it results the data on what works with, more effectively. And it can be applied to the rule for communications, resulting in more efficient and reliable request flow, right? So in addition, service mesh also provide the ability to route requests from failed services and increasing the resiliency. That's what we call the circuit breaking. So let's say if you have multiple services and you see that there are a few pods which are not responding, right? Then if there is a request which is coming to that pod, ultimately and that request can be dependent to different other services. So let's say if that pod is faulty, then it will stop processing the request. Ultimately, your whole circuit of request and response will break. So service mesh can be used for that matter of fact, where it can help you setting up the fault, the circuit breaking. So the next question is like, how does Kubernetes fit in, right? Because Kubernetes is nowadays heavily used in every infrastructure part. So service mesh works on top of Kubernetes, while Kubernetes mainly focus on managing the infrastructure or the application, while the service mesh focus on making the communication among services safe and reliable. Let's talk about the architecture of Istio. Next slide. Okay. So as you can see, service mesh can be split into mainly two components. One is the data plane, the other one is the control plane. The data plane. So these are mainly the sidecar proxies, which are the envoy proxies that are injected into your microservices. These mainly intercept all service to service communication and helps you enabling the application aware features like routing, traffic management, circuit breaking, monitoring, observability, etc., etc. So in simple language, this is the space, I would say, where you can find all of your business-related traffic. The next component is the control plane. This component is the data plane, how to route the traffic within the service mesh. And then this mainly helps dynamically program the proxies sidecar and control the Istio service mesh. So if you open the control plane, there are for the three component mainly who does all of these things, and those component are Pilot, Citadel, Galley. Now in the newer versions of Istio, it is called as the Istio-D. So I'll briefly talk about what are the component and what they specifically do. So the first one is Pilot. It is mainly responsible for managing and configuring the envoy proxies to route traffic internally within the service mesh. The next is Galley. So both Pilot and Galley are responsible for mesh configurations. So they pull the data from the Kubernetes API and mix it with your local configurations, and then push it to different proxies, forming the service mesh. The third one is the Citadel. This is mainly to automate key and certificate management. It pushes the certificates the TLS certificates to services enabling the mutual TLS. So suppose you have your applications which are secured by HTTPS, and then what it mainly does is it validates if the certificates are correct or not, and all of those kind of things. Then we have Mixer. Mixer is mainly responsible for enforcing access control policies and usage policies and collecting the telemetry data from envoy proxies. So here we see that it mainly focusing around policies, right? So what is exactly a policy? Policies are the rules that controls how the system behaves. For example, I'll just give you a quick example of some of the policies that can be implemented. Let's say the quota policies. What should be the the limits of the quota that you have set within your infrastructure. It can be anything like CPU, any sort of resources, right? And then you have different routing rules like load balancing, traffic splitting, request timeout, retry, fault injection, etc., etc. So here, the envoy, which is the proxy sidecar that is injected within the Kubernetes along with your main application pods, it mainly extracts the request level properties from within the Kubernetes cluster and send them to Mixer for evaluation. And Mixer further evaluates it and send those to different backend integrations. So Mixer has mainly like two roles. If I summarize it, it gathers metrics from different components and enforce policies by double checking each request. And in a nutshell, it's mainly like helps to deploying telemetry and policy check. And then yeah, that's it for Mixer. So let's go to next slide. Can we go to next slide, please? Okay, I think it's one before. No, it's one before. Okay, can you go to slide number 32? Okay. So now I'll talk about the data plane component. As you can see in the pictures, there is a request and response flow. So it has following components called gateway, ingress gateway, and then virtual services, destination rules, and then behind the destinations rules, you have your services and pods. So let's quickly understand what these components are. So first one is the ingress gateway. It mainly describes as a load balancer operating at the edge of the service mesh, receiving the incoming or outgoing HTTP or TCP connections. The specifications describe a set of ports that should be exposed, the type of protocol to be used, the SNI configurations for the load balancer, and many other things. What is a virtual service? It mainly defines a set of traffic routes, traffic routing rules to apply when a host is addressed. Each routing rule defines matching criteria for traffic of a specific protocol. So let's say if the traffic is matched, then it is sent to a named destination service, which is defined in your configurations, or subset of the services defined in the registry. The next is the destination rules. It defines the policies that applies to traffic intended for a service after routing has occurred. So these rules specify configurations for load balancing, connection pool size, the outlier detection settings to detect and evict the unhealthy host from the load balancing pool. Next slide. Okay. So now I would like to talk about the some of the areas of observability which is provided by Istio. So if we talk about the observability part, then Istio generates the following type of telemetry in order to provide overall service mesh observability. So there are mainly three three components, which has the observability covered up. These you can see in the screen as metrics, distributed traces, and the access log. Metrics, as you can understand by its name, it mainly generates a set of service metrics based on four golden signals of monitoring, which is latency, error, traffic, and saturations. It also Istio also provides detailed metrics for the mesh control plane, right? The next is the distributed traces. Istio generates distributed traces span for each services, providing operators with a detailed understanding of a call flow and service dependencies within a mesh. So how the request has come from one span to a different span and at the end reached to its destination. It is covered by enabling the traces. The last one is the access log. So as traffic flows into a service within a mesh, Istio can generate a full record of each request, including source and destination metadata. This information enables operators to audit the behavior of the individual services and then act accordingly. So if you go to the next slide, you can see some of the examples of proxy level metrics. Here you can see we have the internal upstream request, and where we gather response code and then cluster name, and you can also have some other attributes of it. And likewise, you also have the upstream request completed, and then you have SSL connection error, many other metrics which you can use in order to analyze the overall performance and observability of your infrastructure. The next is the service level metrics, right? If you go to the next slide, you can see we have certain attributes to service level metrics. It mainly defines the source and destination request flow, and it has certain attributes like what is the destination app, what is this source app, the response code, the workload, and all of the necessary attribute that you can use to analyze the overall performance of your application or request. And then in the next slide, you see the distributed traces of request. So as we can see, Istio can also be used to generate the traces of a request, which can be very helpful for you to understand how the service is behaving, and can further, analyze your application performances in each layer, and can further understand how it works. And in the next slide, you see the access logs. This you can collect and can understand how the request has what is there in the request, and what are the attributes that's there, and that's how you can use access log to further understand your request flow. Next slide. So there are certain standard metrics that Istio provide, but obviously you can customize the metrics as per your need. But these are the standard metrics that Istio comes up by default. The first one is the HTTP metrics, and the other one is the TCP traffic. You can see we have some basic metrics like request count, request size, response size, the message count, and so on and so forth. For the TCP also, we have how many TCP bytes sent. You can also see the byte received, when was the connection open, it got closed, and all of those things. Next, please. So as you can see, Istio comes up with a really great integration with the open source observability tools, which can help you analyze the overall request service to service communication within your microservices by using some great open source tools. As you can see, there are few that I have mentioned, which is Prometheus, Grafana, Zipkin, Sager, Kiali. So you already know, like these are the open source tools which can be used to collect the metrics for the visualization, for the tracing, and all of those all of the similar need. So in the next slide, I have shown a few sample Grafana dashboards, which has come out through the Istio observability. As you can see, we have client request volume, the success rate. It can be categorized with 5xx, 4xx. It can be like server side or client side responses. And then you have request volumes, and then the request durations, the server request durations, and so on and so forth. And in the next slide, again, you can see a different set of Grafana dashboard that has different set of metrics at the service level. So yeah, that's it. I mean, overall, what I wanted to show you is that as your infrastructure grows, and it's kind of very difficult to understand how you can observe and monitor your microservices at scale. And Istio or any service mesh can be really helpful for you to achieve service-to-service communications, and also a great observability within your microservices, and that can help you analyzing how a request is flowing, what is the behavior of your application, what are the things that you can do to improve the latency, the response time, and all of the basic attribute that is required for a great user experience. So that's it for today. I try to make it short, but if you have any questions, I can answer, or as you know, like I'm currently in remote location, so it's okay if you have any questions. Otherwise, we can take those questions and I can answer them in detail as an offline source. So
thank you so much, Bhavna. Any questions in the room? Woo! Anything on that?
No, not cited, but maybe ask.
Any questions in the room at all? You explained it all perfectly by the looks of it, Bhavna. So thank you so much. There's no questions on the slide though, either. Thank you so much. Woo!
thank you.
Have a lovely evening. Bye. Cool. And next we have Leo. Welcome.
It's supposed to be on the max.
Yeah, you can
It's over here, right? Yeah.
They can hear it?
online for this, and then you use. Where's it gone? Yeah, sorry.
Okay, because I heard that apparently there is an echo for online when using this. So
Yeah, but we can stay only with the blue one, and people online should also hear.
And you shout them.
yeah, you can just shout. All right, so welcome to the last talk of the evening. I'm Leo. I'm Senior DevOps Engineer at SumUp in the Observability team, and I'm speaking about end-to-end visibility through highly distributed tracing. And basically, that is a little bit of like a rundown of a project that we've been doing in SumUp this last quarter, trying to bring distributed tracing to our embedded terminals. So if you go to the next slide, the agenda is pretty brief. So I'll give you a little bit of a background and a little bit of motivation on why we're doing this, then go over the approach of how we did it and what challenges we faced. And finally, I'll close with some learnings and potential future work that is left there. So first of all, you might be asking yourself, what is like highly distributed tracing? It's not really a term that has been coined yet. I kind of took that on my own. And in order to define that, let's first take a step back. So let's imagine you run like a web shop, right? You sell little, I don't know, shoes or flowers or something similar to our SumUp merchants. And you have a website that your customers can access through, let's say, through their mobile phone, right? And requests would come in, and the interactions do look something like this, right? You have your little backend, and that serves all the requests. And this is 2022, and we're all DevOps engineers, so very obviously you run your little web shop using microservices. And then the setup suddenly looks like this, right? You have not a single backend that is a monolith, but you have your in green that is like a front end for backend application, and then you have your IAM, user management, email addresses, passwords, all in that yellow component. You have your checkout service that is a separate thing again, and you have some kind of notification service that is used to send confirmation emails, for example. Now, if you want to know about the performance of your backend, of your services, and especially what the, let's say, user perceived quality of the services, you are very likely very interested in how single requests travel through your system, right? This is what we've been discussing before. So if you go to the next slide, you can instrument your backend using, for example, the automatic instrumentation that we've heard about before, or you may be using a service mesh that is automatically instrumented like Istio, like we also heard before. And now you get visibility into your backend. And the whole thing starts kind of looking like this, where a single request coming into the green component, that is like a checkout request, for example. And the first thing it does is check the user's credentials, making sure they're logged in. Then you have your checkout process, and then you have, let's say, a confirmation email being sent. And by instrumenting that architecture, you get these traces in the end, right? We've also seen pictures of those before. It's just like a graphic for that. But this is not really the whole story, right? Because you may want to know what the actual customer is up to. And if you go to the next slide, you could say that tracing your backend is probably enough when all you build is the backend. But at SumUp, we don't. So we have these, go to the next. We have these millions of merchants that use our devices that we build, design, and engineer. Actually, we don't build them in-house, we engineer and design them in-house, and then they get built somewhere else. But they use these devices to sell products themselves, for example, right? And for these millions of merchants that are distributed all around the world, the interactions with SumUp don't start on some website that we host. They start basically as soon as they touch the device, right? Because this is essentially still a piece of our infrastructure. So this is where the distributed tracing suddenly turns into highly distributed tracing, right? If you want to know the interactions that your merchants are having, or the the experiences that your merchants are having with your system, you want to start tracing as early as possible. And in our case, that means we cannot only trace the back end or the front end, we actually want all of it, like front to back and everything in between. So yeah, you can go to the next. With this out of the way, that is like a little bit of a rundown of what I mean by highly distributed tracing. So now let's jump into the approach and the challenges that we faced while instrumenting the embedded devices that we have. So the device that I'm talking about specifically today is Solo. It's like a new card reader that was released sometime late last year. Fully engineered at SumUp in-house. We have a great hardware team that's working there and also in Brazil. It has Wi-Fi and cellular connectivity, hence the name. It doesn't need a mobile phone to connect to our backend. Specifically, the cellular is interesting in this case because customers or merchants better don't actually pay for that data. It has like an infinite data plan kind of, and SumUp is paying for the data, which is something that becomes more important later. Basically, the device is like by the way, it looks like this, not with the wires because this is like a development unit, but it's basically a small Linux computer, right? So surprisingly powerful for the stuff that it's supposed to do. And it runs a main application that is written in C. So if we want to instrument that, the obvious choice, given that it's like the new industry standard and also that good SDKs are readily available, would be OpenTelemetry. So if we want to do that, then we suddenly start facing the very first challenge, which is that the OpenTelemetry SDK is actually written in C++, which is not directly compatible with C. So in order to solve that challenge, we had to create a static library that just exposes a C API. And this library basically manages the complete state of the SDK on the device. That means the tracer, the processor, and the exporter. And those are these three components that are inside the SDK, where the tracer is responsible for creating new spans, storing them, potentially adding attributes to them. And the processor is the part that processes these spans in some way. For example, batches them up into a single trace before sending them off. And then the exporter is basically just an HTTP client that takes the data that you've created and sends it to some tracing backend, for example, some collector. We also added a very small span storage in there so that we can expose a very, very simple API. So usually when you instrument services using OpenTelemetry, you would have to pass we've heard that before, like you have to pass the context through every function call, and that is a real pain in the rear. So what we've been doing is kind of manipulating that API so that by stacking these spans in a single storage, you always only have access to the last one that was created. So you can use like global functions, and it's basically defined as global singletons, if you want, where you access only ever the last span, and you don't have to actually pass the whole context for every function call. You just call globally available functions to manipulate the span. So that is the second challenge that we're facing, because with this design, we only ever have access to the last span, to one span at a time, which in our case is not really a big problem because the application running on Solo is actually single threaded. So there is no backend processing going on. We don't ever, at the moment, need access to more than one span at a time. But that might change in the future. So this was like a deliberate design decision that we made to only get access to the last span, because that's all we need right now. Next slide, please. So diving deeper into the SDK itself, there are two other challenges that we've been facing, namely that the processor is too indeterministic. And that means, in our case, that we have no control over when the SDK decides to take spans and send them off to the backend. And as I said before, we're paying for all the data that is being sent off from Solo, and inadvertently also for all the connections that are being made. So we don't want the SDK to suddenly decide for itself to make any calls, potentially interrupting a transaction while it's being processed, right? So what we had to do there was basically create a custom processor that only exports, or that only that batches up all the data, but only ever returns it as soon as we demand it, which is usually at the end of a single transaction. The second challenge that we faced was that the exporter uses a custom client, meaning that it has its own implementation of HTTP, it links its own libraries, and this is a device that transacts financial data. So the regulations on this are pretty high, and we cannot just use any kind of code base to send data off. So we actually have to make sure that all the data goes through libraries that we have been written, or that we've been writing, or that have been approved by auditors before. So in order to solve this problem, we actually decided to not use the SDK's exporter at all, and basically hand the trace data back into the main app, from where it is then exported as basically the last step of a transaction. So you can go to the next slide. With all of that implemented and tracing basically working in a test environment, we started looking at the data overhead, and the SDK basically works with two different protocols that you can use to send data to your backend. And that is either JSON or OTLP, which is the Open Telemetry something line protocol, I think, which is a protobuf based binary protocol. And then we looked at two different cases, namely exporting only traces or exporting traces with certain attributes that we are interested in. For example, battery levels, network connectivity, all these things that can potentially influence the performance or the experience of a transaction. And to, I guess, nobody's surprise, the binary protocol is much lighter. And also, if you don't send a lot of data, then, well, you don't send a lot of data. And if you don't include attributes in your trace data, then you're kind of reducing that. Next slide, please. Problematic is that even at this almost unusable level of data minimalization, we're still sending about 4 times as much data as a single transaction takes to process, which at scale becomes very costly very, very quickly. And unfortunately, there is not really a good solution to this using just the OpenTelemetry provided tools. Like the things that you would then start looking into would be either, we'll see that later, but sampling, for example, would be one of these solutions there. If you go to the next slide. Lastly, we looked at the collector performance. So basically running a load test against the OpenTelemetry collector, just seeing whether it can actually withstand the load of potentially thousands of clients calling it all at once. So in this example, in this graph, we see a collector being deployed with 2 virtual CPUs and 8 GB of memory, which is pretty low, I would say, comparing the amount of resources that we have basically at our fingertips in the cloud. And we can also see that it can, to some degree, withstand up to 5,000 clients and 2,500 traces being sent per second. This is a benchmark that I've also ran outside of work. If you're interested in more results, a little bit of a advertisement there, you can find it on my blog. But if you go to the next slide, that is kind of the approach and the challenges that we faced wrapped up. And now for some learnings there. Yep, you can go to the next one. So the OpenTelemetry SDK, we can say for an embedded context, it's a good start. Like, it lets you do POC implementations, but it's not perfect, and it's probably not ready to be used in production, which is, I guess, fair to say, considering that it was never designed to work that way. Like, there are still companies running C++ in the backend, and I guess this is what the SDK would rather fit in instead of like a small embedded device. So the learning there would be to rather than using the OpenTelemetry SDK, just consider implementing the limited amount of needed functionality on your own. Like, you don't need to create any custom processors or exporters that way. You probably don't need to wrap everything in a C library, and you can probably save that large footprint of over 30 megabytes of memory that actually has to be loaded just to run the SDK. Secondly, the OTLP protocol, while very lightweight, even its binary representation, is still too generic for this low data lightweight implementation. So the only way around that, really, if you need all these events, you need to have a custom protocol that basically encodes all the possible values that you can have in some way and then reduces them down to single integers or bits or bytes or whatever, instead of having basically a self-describing protocol that Protobuf creates. The last one, not the last one, the third one is a good learning that the Open Telemetry Collector is actually fast enough to handle a lot of clients. And if you're running a highly distributed workload with many of these on your edge, you will probably not face any scalability issues. Considering also that the collector itself is pretty stateless, you can easily scale it out. So this shouldn't be an issue for any highly distributed endeavors that you might embark on. And lastly, we have sampling strategy. This is something that we haven't really touched base on, because in my humble opinion, this is like a new can of worms if you that you have to open and kind of work with if you're talking about like a highly distributed setup. Because well, we haven't talked about it this evening at all, so I'll just give you a quick rundown of like different sampling strategies that you might use to reduce the amount of data that you have to ingest, right? So sampling itself is a strategy where you selectively pick events that are interesting to you. And there is basically right now two strategies. The first one is being head-based, where at the time of data creation, you decide whether you want to keep that data point or not. Let's say you have a transaction that takes more than a second. So you decide, okay, this is too slow. We need to know what's up with that. So we send it off to the backend. But in order to actually make that conclusive, your data and your transactions need to have already passed that trace context. So in cases where you actually don't send off that data to your backend, you're going to run into a problem where your data that you're receiving in the backend is not conclusive anymore, because it's like your traces are missing spans. Basically, you're saying, well, I wanted the whole flow from start to end, but the start kind of decided on its own that it's not interesting enough. So I'm completely missing that part of the picture, which is something you don't really want. So to counter that, you can use tail-based sampling, which is basically the strategy where all the data passes through a single component, and then this single component makes a decision once it has all the data to decide whether the data is worth keeping or not. The problem with that is it's a single component. It's not only a single point of failure, but it also means all the data actually has to get there first. So let's say we have merchants in the US and we have data centers in the US where we actually want to see the spans, but our sampling processing, because most of our markets are in Europe, is also in Europe. That means all the sampling, all the trace data has to go from the US to Europe first and then back to the US, which is, well, not really scalable, right? Like in tail-based sampling, you're basically trading off the statistical accuracy that you get with tail-based sampling for the scalability limitations that you have. So there, the single one learning is we need more research in some way. So if anyone is out there, do it, or we do it ourselves. Yeah, that's it. Thank you for your attention. And if you have any questions. Yeah, I think if you just.
I'm just curious about what kind of data do you pass from the machine to your tracing thing?
So the data that we're passing back is, well, the trace data is really just timings, right? So processing a transaction takes multiple steps. For example, entering a a secure state that is like using special parts of the processor. And we don't get any insights into those, obviously, because they are made to be secure and you cannot see anything inside them. But we can know when they start and when they finish, and things like these, for example. And then the additional data that we add to our traces, the attributes, for example, as I said before, is like battery level, Wi-Fi connectivity, cellular connectivity, stuff like that. Generally things that may potentially impact the merchant's experience when making a transaction. So let's say we realize that transactions are particularly slow for certain merchants for some reason, but we don't know exactly why. Well, with this approach, we would be able to tell if it was actually rolled out to production at some point. We would be able to tell, well, maybe it's because of their shitty cellular connectivity somewhere in the mountains of wherever, right? Could be anything, but this data will hopefully be conclusive to actually tell us these things. So it's not, in case your question was going there, we're not actually, like in that case, we're not actually caring about like data of the transaction itself, like amount of money or who that merchant was, for example. It's really just like machine statistics, right? Yep. I'll just go for you first and then.
Hello. How do you deal with interruption of transaction? Do you have any kind of messaging queue or buffer, or do you, I don't know, have any strategies how to deal with data loss?
You mean interruption in the backend or on the device? So the device itself doesn't use a message queue yet. I have heard there may be plans to do something like that, which is also why I put down the only having access to a single span at a time as a challenge, because the device itself is pretty capable. It can run multi-threaded applications. It just doesn't at the moment. So if a transaction is interrupted for whatever reason, then I honestly cannot tell you what happens. And I guess it just starts from the beginning. So yeah, there was someone in the back there. Yeah, I'll just yeet it over to you. No.
So thank you. I'm from Brazil, so my last company was Rede. I don't know if you know, Rede Card is the same type of company, and we are in I think last 6 months ago, we're implementing collecting logs from the machines, and we have a huge problem with Pci Compliance. So I was just wondering if you have any problems with Pci. Even though we are not storing any Pci logs, the company says, well, you cannot go store these logs because it's Pci compliance machine. So I was wondering if you have the same issue. So
good. Pci compliance, good question. So the one thing where this was relevant for us in this process specifically was when we decided to have the data being passed back into the main app and use our own libraries to send it off to the backend, because PCI scope as it is defined technically means that, or let's start the other way. We are certified for certain connections between the device and our backends. And these connections are defined as, I don't know what, to be honest, exactly, but parts of that is, for example, like the SSL certificates that we use, which means going on from that, we cannot make calls to other backends other than not only our own, but only the ones that we have actually already been certified for, which use the exact certificates that were used in the certification. So that is one of the reasons why we did that, just to make sure that everything there is on the correct data path. We could get recertified eventually if we decide to roll this out to also include calls to like a separate tracing backend, for example. In terms of PCI compliance in our backend, good question. Since this is not touching any merchant data, I would assume this is not an issue, but none of this data is leaving us anyway. So in our case, wouldn't be an issue. I hope. So jokes aside, because this is serious, right? This has never been rolled out to production. This is like very early POC phase, kind of where we test stuff out. So there is no impact anyway.
Why did you decide to use the Open Telemetry SDK if you needed to create a wrapper around it and then also couldn't use the upload functionality and couldn't use the actual back end of it? You completely replaced every part of it, and then why you would choose it in the first place?
We chose that because we needed to get started somewhere. And this is a big company, but with a lot of high priority things. And this was more like a test project first to find out what's possible. So we wanted to get somewhere fairly fast and then see what approach would be more viable. So rewriting everything for a POC is kind of not a good solution for that, right? We had a limited amount of time and limited amount of resources and people that were actually able to work on this. I myself am not an embedded developer, so I was always working with someone from the hardware team to actually make most of these implementations. So that's kind of the reason why. Yeah. Nani was first, sorry.
Yeah, thank you. Yeah, like a follow-up. So you made a lot of very interesting things. Did you think that it can be valuable to share that, to create a community? Because your presentation gives a lot of information about Internet of Things. So, and it seems that it's not touched at all. So in open telemetry. So.
Yes. That's it. No, like, for example, the benchmarking of the collector, right? That was like part of this project. It was like aspiring for it, but this was actually done almost a year ago, actually the beginning of this year, way before this project even started, because I was like, I'm very curious about that. And I would like to see this like maybe become a thing, an Internet of Things kind of thing, you know? Yeah. That's it. So,
so I mean, I know this is a proof of concept. You said that already, but did you gather any insights on things? Did you solve any problems, even in the POC, just by gathering the data and seeing what your little things are doing?
yes. Also, yes. Interestingly, the component that was sometimes very slow, or the part of the process that is sometimes very slow for some reason, was just the gathering of the data for the status of the cellular modem. So whenever you make a transaction, the device checks that it has cellular connectivity, for example. And just by gathering those statistics, we made calls to check that data. And sometimes it turns out this gathering is very slow because apparently the drivers underneath start actually checking these connections even when we're just asking for like signal strength or something like that. So sometimes they're fast, sometimes they're slow. And this is now something that the hardware team has to debug on their own, unfortunately. Poor guys and girls. Yeah, that was one example from the top of my head that I can tell you. Yeah. Any more? Okay. I'll just throw it like this.
Yeah, at the benchmark graph, I noticed there was a sudden downfall and then a rise up again. I was just curious, was it just a coincidence with no traffic or what happened there?
Good throw. The benchmark, like the dip in the end, you mean, right? Yeah, that is with the red line, that is the exact moment that the collector crashes under load. So as soon as it starts becoming unavailable, the red line indicates the first error being returned. So the benchmark works in a way where we have, like, we spin up these clients, thousands of them, send data to the collector, and the collector is configured to send them back to the benchmarking client, which then tells each individual worker, okay, your trace has been processed now. And then as soon as the first worker receives an error, for example, because the data never comes back, that's when we notice, okay, collector is now processing faulty data in some way, that's as much as we can get.
Perfect. I have a final comment. Thank you for organizing this ammonia and also summer for the super amazing sundown meetup. And also thank you for the speakers. I'm colleague of Nadia and it's like great extra for tonight. So thank you for taking the time. Thank you for preparing everything. It was super nice to also be able to present in person. As well as stay in here if you have more questions. We have to support her and want to know how to work at North Town or career opportunities. In case you want to work in the cloud, please refer them. Yeah, so give it up for Leo and all of our speakers, please.
Been absolutely fantastic to have you all here tonight. Thank you so much for coming. We've got pizza, so please stay, please eat. Otherwise it'll go to waste. No, I don't want that. Would be super grateful, really important for us here at Women in DevOps and Trinovo Group that when we're putting on these events, we get your really honest feedback. Scan this QR code, it's literally free, yes or no questions. So I promise it's not going to be annoying, it's super quick, really appreciate it. Please make the most of our wonderful speakers who are here today, ask them questions. And if you've got any questions for me, let me know. But great to meet you all. Let's get the pizza out, help yourself to some drinks, and yeah, thanks for coming.